Well, I'm going to try and convince you that bright red variable stars should not be given up on, despite the fact that they have lost favor in recent years. One of the more spectacular events that's been witnessed in several centuries was Tycho's supernova, which was in fact discovered by Schuler a few days before Tycho first observed it. And one of the nice things about this is that it was bright enough to be seen with the unaided eye for about a year and a half, becoming brighter than Venus at maximum light. And it was recorded, or for posterity, we also have it celebrated in Shakespeare's Hamlet, as in the beginning scenes of Hamlet. I'm showing the Classics Illustrated more for nostalgia purposes than anything else. My mother threw away my collection of Classics Illustrated. But it's also recorded in Edgar Allan Poe's poem El Araf. So wouldn't it be nice to have a spectacular event like this, not only that you see it, but it's recorded for posterity? So now the interesting thing is that Tycho supernova is believed to have been a type 1 supernova, but the type 2s are almost as spectacular, and they're a little bit more easy to predict in a sense of where we should look to see them. We believe that the type 2 supernova come from the evolution, core collapse of massive stars, somewhere in the range between 15 and 25 solar masses. The stars that have evolved well away from the main sequence on the left here in the diagram to the red supergiant region. And they're the ones that are going to go kablooey. The only problem is that when we look at nearby galaxies over the last several decades, we find that supernova 1987A did not originate from an M supergiant. It came from a B3 supergiant, maybe 18 solar masses. Whoop-de-doo. The supernova 1993J and M81 apparently originated from a K8 to G5 supergiant, according to the colors, 17 solar masses maybe. Close, but still no cigar. And of course, supernova 2011 last year in M51 was apparently an FG supergiant. What's going wrong here? Are we looking in the wrong place? I mean, surely, if we're going to look anywhere to see the next supergiant or the next supernova, it ought to come from one of the nearby M supergiants that we can see, and maybe something like Betelgeuse or Cephei. Both are quite bright, for example. And the intriguing thing, of course, is that both these objects are what we call type C semi-regular variables, or SRCs for short. And less regular M supergiant variables go by the name of LC. And I'm not sure if there are any M supergiants which are not variable. That I'm not entirely certain of. Now, the intriguing thing is that if there's going to become a supernova explosion, is there going to be any signature beforehand that we can use later to look for the next one after that? And we don't really know that much about these objects to begin with. The SRC variables, the number cataloged is relatively small, the same with the LC variables. And we have some information. They have long periods, 100 to 1,000 days, maybe secondary periods in excess of 1,000 days. We know their spectral types. We know their luminosity classes. The type C semi-regulars tend to have larger amplitudes than the LCs, both rather unusual. But according to Mike Pierce, back a decade ago, the M supergiants are believed to be at 100 times more common than Cepheids in galaxies, and so might be better distance indicators than Cepheids are. They also seem to obey their own period luminosity relation, quotation marks. And the reason is because if you look at the period luminosity relation as it existed then, it wasn't that great. There's a lot of scatter in there, and not the kind of thing that would be great, although it's been used to determine distances to nearby galaxies. So most of what we know about the periodic M supergiant variables comes from the study of their light curves, and this is a sort of a state of the art which is growing. To give you some idea of what typical light curves are like, these are from eye estimates off photographic plates that I made several years ago in the Harvard plate stacks. Here's CL Carini showing you that its 512-day period is superposed upon what looks like changes in mean brightness, gradual changes in mean brightness. IX Carini is an even more exotic object, a period of almost a year, where it seems to have a larger amplitude when it brightens. I can't explain that. So there are these problems which exist. We also have the AAVSO estimates for objects like VX Sagittarii, sorry. This is an exotic object which I know of at least one professional astronomer who believes that this is a Mira variable despite its M supergiant classification. And as Persei, with a period of 810 days, was noted in a JAAVSO paper not that long ago, actually. My start in this sort of began with an open cluster. I'm actually an open cluster person. I'm here in disguise. And I study open clusters and Cepheid variables. And I was interested in Berkeley 87 because it has an exotic Wolf-Rayet star in it, which is why I studied it. But it also has the red supergiant, BC Sig. And I have managed to gather some observations of BC Sig from the Harvard plate stacks. Here they are melded with estimates from the Sternberg collection as well from Russia. It has a period of about 700 days. It's also been observed quite regularly by AAVSO members over the years, and you can sort of see the changes you can see that, except for the magnitude shift because the differences between the blue and the visual, you can see that the regular pulsation or whatever it is that's taking place is there. The problem is that if you look at the recent AAVSO brightness estimates, there's a large scatter there, which is rather annoying and difficult to get rid of when you're trying to find times of light maximum taking place. The scatter is about a half a magnitude. I'll come back to that in a moment. But in fact, there are a lot of good observers in the AAVSO with making visual eye estimates. I noticed that when I compared what you can do with a color index by forming the differences between the blue and the visual eye estimates for times in common between the different sets of observations. You can see that there are some very good data points there. The color of the star shouldn't change that much. The temperature doesn't change that much over its cycle. And you can see some intrigue. So there's one particular observer who was right on, if you like, and a lot of others, however, were a bit off. I've observed BC Sig spectroscopically as well. It's an interesting object to observe with the spectrograph. The temperature changes can be deduced from the depth of those strong titanium oxide bands. And the luminosity class is a little bit more difficult. You have to go right into the spectrum and find those little luminosity-sensitive features like the ratios of vanadium-1 and yttrium-2 to the nearby iron-1 lines. That can be done with some difficulty. Now, I've also found a problem with the period, finding a good period for these long-period variables. I found, by trial and error, I came up with this method myself, namely keeping track of when light maximum occurred as a function of the cycle number. And it came out quite nice. I get a period here of about 693 days. Just by doing that, by combining both the plate estimates that I made at Harvard and the AAVSO visual eye estimates, finding times of light maximum. There's a lot of scatter, however, in that technique, because it's not always that easy to determine the time of maximum, within a few days. You're usually got within a few weeks, typically, is the problem. And there's two things that affect this. There's the data themselves actually produce some of these variations, and these exotic things which have long periods actually undergo themselves changes in period from one cycle to another. It's a mechanism that there's a little bit of chaos in the mechanism that produces the variability in these objects. Now, many years before that, I'd actually deduced periods for the object using Fourier techniques. And for BC Sig, if you average the data over different time intervals, it looked like there was a period decrease taking place. Around 1900, the period was about 700 days, but in more recent years, it's been closer to about 692 days or something like that. If that's the case, the only reason why an object which is probably pulsating would undergo a period decrease would be if it's getting smaller in size. There's a relationship between the period of an object and how big it is. If BC Sig was getting smaller, that would mean that it should also be getting hotter. And in fact, you can see that there's a direct correlation. The mean brightness of the object has, in fact, increased in that time period. If that's the case, then maybe it will become the next supernova, because it's heading upwards in the HR diagram towards a point that it's getting cooler, it's getting more luminous. Maybe it will become, except it's just decreasing in size. It's a little bit of an anomaly there. However, I still have, I think, December 2012 in the office lottery for when Betelgeuse is going to become a supernova, so I don't know. The intriguing thing is that when you get the right period, now you can actually phase correctly all the other observations you have, particularly the spectroscopic observations. And here I can have phased for BC Sig the spectroscopic observations with showing the temperature variations and the radial velocity variations. And the interesting thing is that it looks like a Cepheid in terms of its variability. The light maximum occurs not when it is hottest and smallest, but a little bit after that. But I'd like to try and do the same thing for something like mu Cephei. You know, can we treat mu Cephei in the same way that I've done as for BC Sig? And that I'm not sure of. Here's the problem. We've got the reverse situation here. We have, for mu Cephei, it's on the edge of the open cluster Trumpler 37. Strangely enough, for most open clusters, I don't know why this is, but the most massive stars are often found on the peripheries of these open clusters. So we know we can actually find the luminosity for mu Cephei from membership in Trumpler 37. Here's a typical way of doing it. Here's the HR diagram for Trumpler 37. That lone point off to the right there is mu Cephei, and implying that it has an incredible luminosity of about -8 in visually. This would be an object which would be up there around 25 solar masses. But we don't know the period very well. Here's some observations that collected by McLaughlin in 1946. You can see the variability taking place, blah, 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 blah. If you look at it more closely, it gets a little bit more interesting. Here's some light variations collected by John Percy with a robotic telescope about a decade ago, showing the light variability of mu Cephei, and you can see some horrible things in there, namely that it looks like there's more than one periodicity present. By chance, the observations here overlapped with observations being made by the Hipparchus telescope, and you can see an offset here. This is a typical problem. Actually, John Percy didn't cite the actual magnitudes for mu Cephei. He did differential photometry. All I did was add the brightness for the comparison star that he used, and you can see that typically this is a problem we have with very red stars, getting the proper standardization and 0 point, taking into account color terms and things like that. There are AAVSO-I estimates, and you can see that back in the early years, near the top, there were a few good observers, apparently, but in more recent years, we've got a smattering of data points which have a scatter of about plus or minus half a magnitude. It's just so frustrating that I got to the point of saying, well, I can do this myself, maybe. But there was a study done by Mantegazza in 1982, did a period analysis of a set of data, and he found two periods, a long period of about 5,000 days and a shorter one of about 881. The top part of the diagram are the observations he used. The middle part is his fitted light curve with the two periods, and the bottom one is his mean for the top part of the diagram. Not a particularly great match, is it? But at least it opened my eyes to the possibility there might be two periods present. So I tried to do something similar myself, actually trying the same technique, counting cycles. You could actually identify the main periodicity because it's sawtooth. The second periodicity is more rounded, and identify which maxima are actually caused by the primary cycle and which are caused by the secondary cycle. And I got two periods, about 105 days and 707 days. If you take the average between the two, you get about 850 days, which is what you get when you throw all the data into a Fourier analysis. You get a period of about 850 days. But is the true period more likely to be 1,000 days? This is the thing I want to ask. Well, I've been observing it, and my observations are the yellow dots here. The white dots are simply from the Hipparchus data shifted to fit the, well, with the phasing using a 1,005-day period. And the blue crosses are what the recent AAVSO observers have been getting. It's interesting that this actually gives a reasonably good fit. In other words, maybe a period of 1,005 days is not that bad. The only problem is, as you can see, there is one big flaw. Namely, that light maximum should occur at phase 0, not a quarter of a cycle later, as it appears to be in this case. But I don't know. I'm continuing to follow this. I got interested in this because it's right next to Delta Cephei in the sky. And I've been observing Delta Cephei on my own for several years. I know, for example, that the 1,004-day or 1,005-day period actually gives a good fit to the old observations by Bob Wing with spectrophotometry of the star made back in the 1970s. It's also true that mu Cephei, when you plot its luminosity with the new period, actually fits the Cepheid period luminosity relation. In fact, remarkably well. The points on the left, the white points and the yellow points, are Cepheids in open clusters and measured, also ones measured with the Hubble Space Telescope. And the green points are SRC variables in open clusters. There's lots of them. Mu Cephei is the longest period object in that sample. There's another way of looking at this, and that is to say, well, look at all the deviating green points. Maybe that's a consequence of mass loss, because the difference between type 2 Cepheids, the blue objects in this picture, and the type 1 Cepheids is basically one of mass. The type 1 Cepheids are massive stars anywhere from 4 to 15 or so solar masses, whereas the type 2 Cepheids are presumably less than about a solar mass. And so if we have M supergiants losing mass, maybe they are become less luminous as a consequence. But we still have a lot to learn. We're only in the beginning stages of this, and I have no idea what mu Cephei is going to do next. It's kind of catchy to get started in this. As I say, I set up my own sequence to observe Delta Cephei many years ago, and I've simply been adding in observations of mu Cephei in the last year. And in the time that I've been observing it, close to a year now, it has faded from 4th magnitude to a whopping 4.3, or maybe 4.4. Not much change in the course of a year. It's not something you can get terribly excited about, but on the other hand, you don't have to worry about missing a night or two of observation, because it's unlikely to do much in that time period. So if anyone is interested in it, please speak to me, and I'll try and twist your arm. Thank you. That's a good idea. I don't happen to have one. I'm still using, by the way, my yeah, or even video cameras. I know that my colleagues in Ukraine, they go wild about those video cameras that